Okay, good afternoon, everyone. Thank you all for coming. Thank you, Li Hui, for the kind introduction and for hosting me. It's been a great pleasure for me to come and visit IAA, and also it's an honor to present the last colloquium before the Spring Festival break. So today I'm going to present my work during my PhD at the University of Oxford and also the European Southern Observatory in Germany within these great collaborations, the Wisdom project and the ACES project. So I'm going to talk about cold molecular gas properties or gas cloud properties in some nearby galaxies. So now let's get started. This is the outline of my talk. I will first give a brief introduction about cold molecular gas in the context of galaxy evolution. I will also talk about how we observe them with interferometry, especially the ALMA facility. And then I will walk you through three different types of galaxies. First, we'll have a look at the kiloparsec scale gas disks in a few AGN megamaser host galaxies. And then we'll move on to early type galaxies at a smaller spatial scale, where we can actually resolve giant molecular clouds with 10 parsec, 20 parsec-ish spatial resolution. And after that, we will talk about gas clumps at even better resolution in our own Milky Way center. And in the end, I will try to summarize the potential physical drivers of different gas properties across different scales. So to set the stage a bit, I would like to present this classic view of galaxy evolution, especially in the nearby universe. Maybe by today's standards, the Hubble sequence is a little bit out of date. However, I think it's still a good point to make sure we are on the same page about our nearby universe. So on the left-hand side, we define these galaxies as the so-called early type galaxies, which consist of the elliptical galaxies here and also the lenticular S0 galaxies in the middle. And on the right-hand side, we have the late type galaxies. So you can see this morphological bimodality is defined by the spiral arms or prominent bulges or featureless stellar envelopes. So not only the morphologies are different across different types of galaxies, their other properties are also drastically different. For example, for spiral galaxies, when we look at their stellar populations, they are usually relatively young, and they are also very gas-rich. The color of the stellar populations are rather blue, but on the other hand, the early type galaxies, especially the ellipticals, are considered as red and dead galaxies with very little gas left. And also they are different in kinematics or dynamics as well. We will see a bit more in the later parts of the talk. So the big question we want to answer in the field of galaxy evolution is simply how galaxies land in their present-day look. How do they evolve through the cosmic time and now present themselves to us with such a variety of properties? And potentially, is there any evolutionary track or channel across these different types? Or maybe they are evolving by themselves independently and then through different formation channels. And some channels will end up being early types, some channels will end up being late types without crossing different types. These are some of the big questions in the field. In order to understand that, I think another critical perspective to look at a galaxy is actually the individual particles a galaxy harbors. So this is the so-called baryon cycle. Maybe you can start from an arbitrary corner from here. So first, a galaxy would accrete atomic gas from the cosmic filament, for example. This is also called the pristine gas. After a galaxy has got some atomic gas, they concentrate towards the center of the galaxy. They form molecules with the aid of dust grains, for example. And then we have molecular gas, which can be observed by ALMA through line emission or James Webb through continuum emission, for example. Out of the molecular gas, we have newborn stars. These stars are formed in what is called the giant molecular clouds. And also, when stars are born, they would give out feedback to ionize their surrounding gas by ionization. They would blow away their parental molecular clouds. And especially towards the end of their life, They may evolve as planetary nebula, shown here. They may also evolve towards supernovae explosion or supernova remnants. They give away their metallicity, give away their energy and momentum to their surrounding interstellar medium. So the baryon cycle can move onwards, and then next generations of stars will form with different properties. So this is basically how a galaxy evolved through time by different populations of gas and different cycles of baryons. So my research during the PhD is mainly looking at the molecular phase of the gas, because I think it is important in triggering the next generation of star formation, because stars form out of molecular gas rather than any other phase. And also it is the immediate surrounding that bears stellar feedback or AGN feedback, as we will see later. So I think this is a key stage to understand the whole baryon cycle. And also a side note about my upcoming postdoc position is that we will use optical IFU data as well to look at ionized gas, for example, with Muse spectroscopy, and to try to combine molecular phase and ionized phase to understand the interstellar medium and stellar population, galaxy evolution in more details. So moving on to how we actually observe cold molecular gas. The most abundant species of molecular gas is naturally the molecular hydrogen. However, we know molecular hydrogen is symmetric, so they do not emit when they are very cold. So instead, we have to resort to the second most abundant species, which is carbon monoxide. And because it's not symmetric, it does emit even at cold temperatures, which falls into the millimeter wavelength regime. In the past, we only had single-dish telescopes shown here, and they did a very good survey of the integrated properties of molecular content in a galaxy. However, they had relatively poor spatial resolution compared to the interferometric arrays in the recent 1 or 2 decades. So just to briefly introduce the idea of interferometry, when we have an array of telescopes, maybe 10, maybe 50, it no longer observes the sky in the real plane. Instead, it observes the sky in the Fourier space, and then through some software computation, inverse Fourier transform, we can make the Fourier space observation back into the real space, and then we get an image of the sky plane. And due to this technique, actually we can use a baseline of a pair of telescope antenna to work effectively as a huge dish of one single telescope in terms of spatial resolution. So only in terms of angular resolution, the interferometric array is as powerful as a huge dish encompassing the whole baseline. It also has some other caveats, artifacts of the data, more challenges involved, but basically it does allow us to go beyond the local group with such much higher angular resolution than single dish would allow. And the reason we want to go beyond the local group is that we can probe a much wider variety of galaxy types. Because within the local group, we have all of them are spiral galaxies or dwarf galaxies. We don't have any elliptical galaxies or lenticular galaxies, for example. But now with the recent advancement of the observing technologies, we can actually resolve giant molecular clouds at very fine spatial resolution in elliptical galaxies too. So the first high-level question we want to briefly look at is the gas disk morphology dependence on galaxy type. And the short answer would be yes, there is a big difference across different galaxies. As you can see on this plot, the x-axis shows the central stellar mass surface density, which is used as a proxy of galaxy morphological types. You can see here on the left-hand side, it's approximately speaking late-type galaxies, and on the right, we have early-type galaxies. The Gini coefficient basically tells us how uneven the gas intensity distributes in a galaxy. The higher, the more uneven, the lower, the more smooth. So just by eye, by visual inspection, we can see that early types usually have gas disks that are very much smooth. However, the spiral galaxies, we can even see the spiral patterns. They are more clumpy than the early type galaxies. Apart from this morphology, late type galaxies also have higher gas mass fraction. This means about 10% of the stellar mass in a spiral galaxy is usually in the form of molecular gas, more or less. But for early type galaxies, first of all, only a quarter of the early type galaxies still have detectable molecular gas. The rest of 3/4 actually do not have any molecular gas at all. And even within this 1/4 of galaxies with molecular gas, there is only 1% of stellar mass in the form of molecular phase. So this is another huge difference. Also, the spatial scale is quite different. The spiral galaxies usually have molecular gas everywhere in their optical extent. Like you can imagine on a spiral arm, there has to be some molecular gas for the spiral arms to form new stars. However, in early type galaxies, the molecular gas we see here are only concentrated in the very central region of a galaxy. Usually we call them the bulge region of a galaxy, maybe just 1 kiloparsec instead of 10 kiloparsec in size. So this is quite spatially concentrated within the bulge. And then moving on to more specific galaxies, we would first look at some active galaxies at kiloparsec scale. I want to present this galaxy first. This is a spiral galaxy. You can see here the spiral, large-scale spirals, and then a zoom in of this optical image where we have the ALMA field of view detecting the cold molecular gas in the white contours. So the white contours is the same as this map. So on the second row, this is plotting the moment 0 map, moment 1 map, and moment 2 map of the cold molecular observations from ALMA. So the moment 0 map is basically integration along the line of sight to tell us how much gas there is at different locations. And you can immediately see one feature that along this particular direction, we have roughly no gas at all. Or maybe you can see it even more clearly here. Along this direction, we have very little gas. But along this perpendicular direction, we have some decent amount of gas. And in combination with the blue color in this image, the blue color is showing the blue band imaging of this galaxy. We can see that some ionized gas from spectroscopy observations as well, it tells us the active galactic nuclei is actually doing a lot of work along this direction. So this galaxy has been studied previously as well, and other papers reported ionized gas bubbles around this area and this area as well. And also people discovered radial bubbles too. So radial bubbles is another tracer of AGN activities also along this direction, so roughly here and here. So we are pretty sure that the deficit of molecular gas along this particular direction is likely due to AGN feedback. It can either be photodissociation of the CO molecule, it can also be ionization towards higher energy states, or it can just be some depletion in some form of molecular gas. But in any case, we don't observe them here. So a second feature of this galaxy is the disturbed kinematics. You can see in the moment 1 map, this is showing the mean velocity along each line of sight, telling us how the gas disk is rotating. However, the rotation depicted in this image is not very regular. You can compare this with some other galaxies later, but I can show you this is among the most messy velocity field we can have. And this is believed to be due to the 2 bars existent in this galaxy. You can see a large-scale bar, roughly in this orientation, and also people did modeling to find there is also a tiny nuclear bar in the very central region. We can't really see it in the optical image here, but through dynamical modeling, people claim that these 2 bars caused all the kinks in each color of the isovelocity contours, so to speak. So basically, in this galaxy, we see the effect of AGN feedback, we see the effect of bar-driven, non-axisymmetric gravitational potential in the play. The other thing we looked at is with ALMA cold molecular gas observation, we also get continuum for free. So this continuum is showing 2 prominent sources. We also did a spectral index fitting with ALMA sample here and also VLA data here. And the spectral indices of these two blobs are very much consistent with the scenario of an AGN jet being here, approaching us, and also a core of the AGN activity. So this is kind of confirming the previous studies that AGN creates these features in this galaxy. The other galaxy I want to show is another barred galaxy. You can see the grand design bar in this direction, also with spiral arms in the outskirts. So the gas distributes prominently along this line and also along this line. So we call these two parallel lines the parallel dust lanes. They are basically the leading edge of this bar because we think when the bar rotates, it also funnels the gas from kpc scale to the inner 100 pc scale, for example. This is one mechanism we believe gas migrates inwards into a galaxy. And when they land into the very center of the galaxy, in the velocity map, we can see there is a kinematically decoupled core, because if we look at the green curve, we can see in the very center it has a warp. So we call this a regularly rotating core in the very central region of this galaxy, the nuclear disk. So this is another type of behavior that a galaxy can be transported from kpc scale to the inner central region of a galaxy. Yep.
Is it alignment? So it's blue shifted on top, so the top edge is closer to us? Is that alignment? It's a disk, right? So the disk,
yes.
And there's a velocity gradient, meaning it's not perfectly edge on. It's not perfectly face on. It's kind of maybe 30 degrees. And
yep, that's true. Yep.
I think the fact that the top is these are trailing spirals. It's a trailing spiral, right?
I mean this spiral we see here,
trailing, right? Which means that the top being blue means that the top side is closer to us. Is that the right interpretation?
So blue means it's moving towards us.
Yes.
Yeah, I think that's likely the case.
The galaxy has roughly, the one that's closest to us is no shift, but roughly the top left side is closer to us, and the bottom right is further away. And I think this contradicts EA's papers, where he claims that the dust lanes are further away from us, because I see the dust lanes on the top left prominently. So is this a counterexample to EA's work?
I'm not particularly familiar with that piece of work. I would be very interested in reading the paper. But when you mention the dust lane, you mean roughly speaking like here and here, right? Maybe this is not the best image to see it. We do have an unsharp masked image here in the background though. But I think, yeah, it's worth some more detailed comparison. Yeah. So maybe we can move on for the sake of time, and I'm very happy to discuss afterwards. So both of the galaxies I showed here has some peculiar features in morphology, distribution, or kinematics. So we were curious to search in the literature for some other megamaser host galaxies to see if this is a more general trend. So we found 9 galaxies with similar spatial resolution of ALMA or other interferometric arrays, and almost all of them show similar features. It can be inflow or outflow, or it can be kinematic disturbances, or morphological irregularities. So we naturally came up with a conjecture of necessary condition for the megamaser in the very center of the galaxy, which is also related to the accretion disk of the central supermassive black hole. First, we think there is some mechanism that has happened at some point. It can be bar-driven non-axisymmetric potential. It can be the AGN activities. It can be an external galaxy passing by. But due to this external or internal turbulence, the gas infalls from kiloparsec to the center parsec scale, and then it builds up in the very center to be very high in column density or volume density, which further triggers megamaser events and also supermassive black hole feeding. And this might be a typical scenario for megamaser galaxies, but it can also be a general trend for any Seyfert-II AGN galaxies as well. We don't have a large enough sample to tell whether maser galaxies is special in this regard, but we do believe there is some correlation between the gas properties and the AGN activities or maser activities here that is worth further exploration. So moving on to early type galaxies, a different regime, and also a slightly different scientific question to answer, we are curious about how molecular gas forms stars. So first, to briefly present this work, we want to know what suppresses star formation, especially in the central bulge region. So in this galaxy, we have both ALMA observation of cold molecular gas in CO, and also the Seyfert-II spectral graph on board Seyfert-II observations for the H-alpha flux, which tells us about the star formation rate. The classic way to plot is the Kaneka-Schmidt relation. On the y-axis is the star formation rate, on the x-axis is the cold molecular gas available. And we can also plot the depletion time. So maybe we focus on this radial profile a bit more. We can see all the three different curves with slightly different assumptions, but all the three different curves have a higher depletion time when they are closer to the galaxy center. So this means stars are forming less efficiently towards the galactic center or within the bulge region. And this is one evidence that star formation is suppressed in the central region. In this galaxy, we made a few different assumptions and discussed a few different possible scenarios. And in the end, we think the shear effects in the bulge region is probably one of the mechanisms that shuts down star formation. But because the spatial resolution is not enough to resolve gas clouds, so we actually don't know whether gas clouds are different in properties in this particular central region or not. So here comes my project, where we have enough spatial resolution to actually resolve molecular clouds and measure their properties in a different galaxy. This galaxy is a genuine lenticular galaxy or early type galaxy, as I promised. It has a prominent bulge, as you can see in the center. It is in the very center of a Fornax cluster, so that's why it has no atomic gas at all. However, it still has a detectable molecular gas disk, only in the very central part, plotted in the contour. Again, if we look at its moment maps to see the large-scale distribution or kinematics, you can see this galaxy molecular disk is very regularly rotating. And then the intensity map tells us it's slightly more concentrated in the central region of the galaxy compared to the outskirts of the galaxy. So here I say it's a decreasing mass density radial profile. And also for the line width profile, the velocity dispersion profile, it's also higher in the center and slightly lower on the outskirts. But we want to look at individual molecular clouds in this galaxy. So the first thing we calculated was the tumor parameter, which is a probe of disk instability. Because like we said before, early type galaxies usually have a very smooth disk. If the disk is perfectly smooth, we have zero cloud. We have zero overdensities or clumps. But this galaxy does have a relatively low tumor instability parameter for the majority parts of the galaxy. It's almost in the regime of an unstable disk. And indeed, we do identify about 1,500 giant molecular clouds with this algorithm. So the definition of a cloud is quite intuitively just the overdensities in 3D data cubes. So we run the cprops2 algorithm. If you're interested, you can check more detail in the paper. But in the end, we identify these clouds plotted in the ellipsis. And more or less, they agree very well with the virial impression of where we have a higher density, where we have relatively smooth and diffuse gas. So for this catalog of giant molecular clouds, we focus on the resolved ones, roughly 1,100. We measure their basic parameters, the size, the mass, the line width. These are pretty much straightforward, and we plot these one against each other to compare the relations with other systems. So you can see on the first plot, this is the line width versus size relation for all the resolved clouds of this galaxy. And interestingly, when we compare these data points with the lines in the background, we realize they are actually very similar to the Milky Way disk in the black line, rather than similar to the Milky Way center in the orange line. This is quite surprising because before I studied this galaxy, we had a small sample of other galaxies plotted here, and they are color-coded by their Hubble type. And you can see usually the lighter the color is, the lighter the color means the more late type the galaxy is. It usually has a lower size line width relation, very similar to the Milky Way disk again. And the darker color contours means the more early type the galaxy is. And usually they have a higher velocity dispersion, which traces a higher turbulence in the clouds at any given radius. So indeed, compared to this emerging trend, this galaxy 1387 is kind of an outlier for the early type galaxies, the few of the early type galaxies we have studied so far. The similar conclusion can be drawn from the other two panels. This galaxy's clouds are always similar to the black line showing the Milky Way disk trend. However, this is the very center of an early type galaxy, which is not forming stars, as we will see later. So this is quite surprising and puzzling. Another way to look at... Yeah?
The lower left and the upper right, I'm supposed to be looking at the dashed line on the... No, you don't have the Milky Way. So I'm trying to figure out which line I'm supposed to compare between the two. Because you're saying that this is not in the same place as the top right ones, but I can't orient myself. So...
Yeah, so the Milky Way disk cloud population is this light green one.
It's a light green, which is a dotted line in the lower left. Is that
yes, dotted line, yes. Dotted line in the lower left.
A circle there. And then the dashed line is the same as the dotted line on the lower left. That's what I'm reading.
This line is a fitting. This line is a fitting to this galaxy.
For the dotted line.
Oh, you mean the orange?
No,
or
it's a black dotted line on the lower left. It says Milky Way disk.
Yeah.
Okay. And then on the right one, the green circle also has Milky Way disk.
And also this line as well. This line is a fitting to the green circle. So both of
so the dashed line and the dotted line are the same line.
Yeah.
Yes.
I think so.
You think so?
Yeah. Well, different calibrations may be used, but they are more or less within 0.2 dex.
It's your paper, isn't it? You can know for certainty.
I know there is a small difference. People use different calibrations.
No, definitely you use it. It's your paper, both plots.
Oh no, this paper is not my. This plot is borrowed, but these three plots are in my paper.
Maybe you should label it when you borrow a plot.
Oh yeah, sorry. That's a good point.
Yeah, and I'm just confused. Like why if you have the same plot that you made, it's different. But now you answered it. It's somebody else's plot. Thank you.
Oh yeah, that's true. I should put a reference here.
Note that.
Yeah.
When you take somebody else's plot.
Yeah. All right. So I hope I made the point clear that the clouds in this early type galaxy is similar to late type environments. Simon? Mm-hmm. Stellar mass, right? I don't remember the values, the numbers off the top of my head, but 1387 have 5 times 10 to the 10th. So it's a typical lenticular galaxy mass, I would say. It's not a super heavy, super massive or super light. But I need to check for these 4526, for example. I can't remember how massive it is. But yeah, that's a good thing to check. But we do check a few other parameters, and my galaxy is always similar to the general early type population. It's not an outlier in any parameters we have checked. So the same conclusion can be drawn from the virial parameter, which is just another way to combine these basic parameters. It tells us whether the clouds are virialized, whether it's bounded, whether it's long-lived or transient. So in the end, if you look at this histogram, it shows us on average the clouds in this galaxy have alpha equal to 1. So this is log scale. So alpha equal to 1 means perfectly virialized. So this is again different from another early type galaxy. In this galaxy, it has a much higher virial parameter, which means the clouds are likely dispersing in a short time scale because the velocity dispersion is very high. That's why it has a high alpha parameter. And on the other hand, to compare with nearby spiral galaxies or late type galaxies, they usually have lower alpha parameter, virial parameter in the range of 1 to 2. So again, this galaxy is rather similar in virial parameter as well to late type galaxies. And also by definition, it means the clouds should be long-lived and they should be ready to form stars. They have enough time. But actually, it has low star formation efficiency. So the galaxy is in the red circle. You can see 2 points. This means 2 different assumptions of how you use H-alpha flux. But even if we look at this whole range of the potential depletion time of this galaxy, it's still much longer depletion time than the general trend overplotted in the background. This means it's quite low in star formation efficiency. And if we look at it in a spatially resolved version, this is also quite interesting. We have a star-forming dominated ring in this bulge area of the galaxy, still in the very center of the galaxy. And inside this ring, we also have H-alpha flux, but it's dominated by AGN liner emission or dominated by composite mechanisms. So we only plot star-forming ring here. It also corresponds to an optical ring here by another paper. So this might be an inside-out growth scenario of a nuclear disk, but we haven't probed into this direction too much yet. The overlap is quite good because we have CO basically within this whole square region. We have CO everywhere.
And then the Q is exactly less than 1 in the H-alpha? No.
The Q is almost equal to 1 in the outskirts of this field of view. Yes. So in the ring.
Every place where you see H-alpha, it's less than 1, you're saying?
Q is roughly equal to 1.
Equal to 1.
Roughly equal to 1. Yeah. So this is also an interesting direction to probe in the future. But let's move on for now. We start to probe a few potential physical drivers that can shape the cloud properties. But for the sake of time, I will go a bit fast in these few slides. So the first one we looked at is galactic shear. In order to understand galactic shear a bit better, in this paper, my collaborator developed a modified virial theorem to take into account the host galaxy's gravitational potential when we calculate an individual cloud's virial parameter, so to speak. So in another galaxy, 4429, this is not my galaxy. This is the other early type galaxy. After calculating using this modeling, they find excellent agreement between the model prediction and the actually measured effective virial parameter. However, this model is not testable in this galaxy because the inclination is quite different. And because my galaxy 3887, if you remember, is quite face-on. It's almost face-on. So we cannot really probe the in-plane velocity dispersion so well. We can only see through the disk. So indeed, the inclination of the galaxy matters when we talk about velocity dispersions.
What's alpha and alpha mod? What am I looking at?
Alpha effective is a more sophisticated way from the observational data.
And alpha mod?
Alpha model is we assume all the clouds are dominated by shear motion, and then we calculate a analytically predicted virial parameter for the cloud population.
But you did this after you measured, you knew the answer before you modified it.
No, we only know the location of the clouds. We only know the location of their center.
Right? So you can build a model after you have the data, or you can build a model first and then get data. But you're saying you first knew the answer was 2.1, and then you made a model, and that gets 2.0, and that's agreement. Yes.
But the model does not rely on any observations.
What? But you knew the answer.
I actually don't know which happened first. I actually don't know because I'm not part of this paper. I don't know whether they calculated the model first or they calculated the observation first. So I'm not sure. But I get your point. That sometimes we need to watch out when we build a model, yes. So another way to look at the shear effect, despite the inclination, is to look at cloud spin, which is the velocity gradient of each individual cloud. But for the sake of time, I'm afraid I need to skip this part. But the basic idea is that there is a trend across a small sample of galaxies. Some galaxies have clouds almost always aligned with the large-scale kinematic field, velocity field. Some galaxies have a large fraction of retrograde clouds. The clouds are actually kind of anti-parallel, or they rotate in the opposite way of the large-scale kinematic field. But if you're interested, you can ask me later. And then the other model I want to briefly introduce is the cloud collision model. So this is assuming cloud collision is the dominating process to shape cloud properties. And then in this paper, we have a few heuristic derivations to predict velocity dispersion. And again, we claim that the magnitude or the predicted size-line-width relation does match the clouds in this galaxy. So it's a dwarf galaxy. It's another galaxy, but unfortunately, it's not applicable in this galaxy because the angular resolution is not good enough at the moment. So in the last part, I will spend a few minutes to talk about the Milky Way center, our own Milky Way galaxy, at even higher spatial resolution. As part of the ACES survey, it's called the Milky Way Central Molecular Zone Exploration Survey. This is the central molecular zone. You can see in the far infrared from Herschel, it's roughly 200 parsec in spatial extent, the whole zone. And we have spatial resolution of sub-parsec spatial resolution. In my work, I'm only using the 7-meter data of ALMA, which is a lower resolution version of the observation. But in the future, you can look forward to an even much higher spatial resolution when it's available and the science will be out as a follow-up. And here we use a dense gas tracer HNCO, so it's a different molecule. Before, we have always been using CO, carbon monoxide. But in the Milky Way center, we have to use dense gas tracer, otherwise the foreground contamination is too high. And when I decompose the zone, the molecular zone, into clouds, I use a different algorithm. This is called the dendrogram, which means tree plot by face value. It means it no longer assigns pixels uniquely. It is a non-unique structure identification. It has the advantage to capture the nested hierarchical morphology of ISM. There's no magic physical scale of the ISM. It's all the way up to 100 parsec down to sub-parsec scale. And we believe this approach can capture all the different physics going on. And you can see all the contours are encompassing one another because this is like a tree building up different branches, different leaves. And then again, I measure different properties, similar as before. And we want to test whether shear is playing a dominant role. So when I say shear, I mean the rotation curve of a galaxy kind of introduces differential rotation. It means if a cloud is in this red circle, they are hand in hand with each other at the initial point, they actually rotate at different angular velocity. And then after one dynamical scale, for example, it becomes elongated. So what I want to test is using axis ratio to show the magnitude of elongation and using position angle to show the orientation of elongation. And the data points would look like this. I put different size of clumps in different panels, small ones, medium ones, and large ones. The data points are summarized in the magenta line, which is the running mean. And we can see there is a signal kind of emerging here. This happens at a low axis ratio, roughly 0.2, and also it happens at 90-degree position angle, morphologically position angle. This means 90-degree means it's along the galactic plane because we define north as 0. So 90 degrees along the galactic plane. So we say these two happens together. I'll have a summarize a bit later. The other mechanism we looked at is whether magnetic fields are also shaping the morphologies of the clouds. So this is done by polarization data of infrared emission from Sophia, the aeroplane fireplace survey. And we do have the magnetic field strength and also the orientation. So I can plot their orientation, the angle difference, to see whether they are aligned with each other. And I'm also again plotting the axis ratio and morphological position angle here. So I think there is some tentative signal here that when its axis ratio is very low, which means it's strongly elongated, it's also very low in the angle difference. And also, again, when the orientation is along the galactic plane with 90-degree orientation position angle, it also has a very small angle difference, which means good alignment with magnetic fields.
Yeah, it's interesting that magnetic field is aligned with rotation.
Align with morphological position angle, so major axis.
Systematically, the the magnetic fields are not randomly distributed. They have a systematic correlation between the fields are generally also sheared. Meaning, this you would get a signal in the second plot, even if the only mechanism is with, let's say, the only mechanism was that the first plot you showed, that the elongation is in the rotation direction. Then implicitly it will align with phi b because phi b is also aligned. So it does correlation is not causation, right? So
that's exactly my next point.
Yes.
That's exactly my next point. We do see coexistence, but from coexistence or correlation to causality, that's another major leap. The coexistence is among three things: in-plane orientation, which means 90-degree position angle as defined here, large elongation, which means low excess ratio, and a relatively good alignment between magnetic fields and the morphology. But again, we don't know causality yet. There is not strong enough evidence. However, I do believe there is some future in the study because on a small scale, magnetic fields is not perfectly oriented along the parallel to the plane. So I think on small scale, there is some variation that we can leverage to.
Make a 3D plot, right? You've got phi m, phi b, and axis ratios. If you do it in 3D, then you can just take the orthogonal part in that plane. Have you tried that?
Sorry, say that again.
So this is projection. Okay, you've got phi m minus phi b.
Yeah.
But in practice, you actually know phi m and you know phi b, and you know this axis ratio. So in reality, this data set is a 3D data set. Okay, so imagine we plotted phi b, phi m, and then the axis ratio. Okay, and then what you will find is that, well, okay, phi m and phi b are correlated, and the axis ratio may trend in a plane in this three-dimensional space or not. So just plot it in 3D. I think you just know the answer.
Yeah, that's one way to look at it. Yeah, indeed. There are multiple other ways that we should be looking at it in the future. Yeah, this is still ongoing work. So,
but I just suggest it takes 5 minutes to plot, right?
Yeah, although data visualization and also how to interpret the physics would take longer than 5 minutes, but I may only have 5 minutes left. So just for the sake, we also compared the magnetic field strength as well, and also as a function of physical scales. So you can see clouds are defined as larger physical structures, clumps are defined as smaller ones, and then again we look at the difference between these two angles, and we say higher magnetic field strength, lower magnetic field strength. So we have 4 populations. And the 4 populations, 2 of them have flat distribution, 2 of them have peak distribution, although with different peaks. However, this behavior of all the 4 different populations actually agree with theoretical predictions in this paper, for example. This has something to do with physical scale. There is a critical scale above which it's effective. There is also different channels that gas can accrete either along the magnetic field line or perpendicular to the magnetic field line. So this might be a coincidence, but on first look, it does agree. All the 4 population behavior does agree with simulations, which is an encouraging sign. But yeah, I mean, we have seen virial parameter before. So a subsample of the clouds in the Milky Way central molecular zone is subvirial as well as a low turbulence level in the size-line width relation. Again, some of them are quite low in line width. So they may be forming stars in the very near future. And just to summarize what I have talked about, I hope I have shown that molecular gas is fundamental and complex to understand. They also vary across the Hubble sequence of different galaxies. In the 3 projects I have shown, the AGN galaxies are showing very complex features. This might be related to maser events or feeding of the black hole in the center. In early type galaxies, we find one peculiar early type galaxy that have clouds similar to the Milky Way disk, but still has very low star formation efficiency. And in the Milky Way central molecular zone, when we look at the physical driver of the cloud properties, we again find evidence or some correlation, so to speak, among shear effects and magnetic fields to shape gas morphology. So on the last slide I want to summarize these words into another way of this plot I borrowed from a workshop between Heidelberg and Harvard last December. What I have covered in my talk is roughly the right-hand side half of this figure from 1 parsec physical scale to 100 parsec physical scale. and the contribution of different physical processes is quite different from smaller scales and large scales. When we look at even smaller star-forming cores, gravity and thermal supports are dominant. That's why stars can actually form. But when we look at slightly larger scales, turbulence starts to kick in, and turbulence actually can prevent star formation to be going on. And magnetic fields is also becoming more strongly contributing to the picture at starting from some critical scale that I may also have touched upon. So I hope this picture, although it's from 2008 to be honest, but I hope in the near future with more data coming in, we can know more and more details with more and more certainty about this picture. So I will stop here. Thanks for your attention. Happy Lunar New Year.
Thank you for your talk. So you mentioned for this 1387 is in the center of Fuheng.
Yes. Yes.
And you also have the temperature measurement of the molecular cloud.
Temperature measurement would be a bit more difficult. From what I know, people usually use ammonia observed by VLA to measure the temperature of the molecular phase. But I guess maybe in the cluster environment, we also have X-ray measurement, but that's a different phase of the gas.
How about your continuum measurement?
We don't have any continuum detection for dust continuum because it's too faint, I think.
Can you use line ratios? CO line ratios?
We have been proposing for ALMA observations, so if that proposal ends up in any of your desk, maybe we would have a higher chance to get observations for multi-line transition, like spectral line energy distribution modeling, so that we can get the kinetic temperature. Yes, that's one way we have been pursuing.
So you at one point you concluded clouds are hierarchical structure.
Yes.
So how did you define the cloud to start with, and then move on to calculate like a virial parameters? Always say that how you pick up the size of the cloud, define a cloud, without depending on the resolution of your data, you know, or how reliable we can trust.
Yes,
I
yes.
work on that.
Yeah, I understand. This is indeed a hot topic in the field for like 5 years so far. For example, at poor resolution of 100 parsec, the Fuheng's collaboration, which I'm now part of, also measures the so-called cloud scale properties. They have to assume there is one cloud within each beam. There is one cloud inside every 100 parsec circle, for example. And then what they measure is kind of a population average. But when we have 10 parsec resolution, we have slightly more confidence, saying, oh, this is indeed an overdensity. Everything outside it is more diffuse, like diffuse gas. With CPROPs, we do assign all the diffuse gas pixel as well to a cloud structure. So kind of all the pixels are accounted for when we measure these properties. It is quite robust. I do have a slide to show potential variation in the parameters we try. These are two most important parameters. This is the contrast level between the peak and the diffuse gas to define a cloud seed, so to speak. And this is the convexity in geometry of a cloud. It has to be a convex entity rather than a concave entity, kind of. Otherwise, it has too many substructures. So from this practice, we conclude it doesn't change our conclusion, first of all. All of them have alpha equal to 1. So it doesn't change the scientific conclusion, even if we vary the critical parameters. So this is one way. The other way is to actually measure the alpha parameter, for example, as a function of the cloud growth. So for example, if within a cloud we have 16 independent beams, 4 by 4, then we can actually do a growth curve to see how the cloud core, the cloud peak, changes when we go towards the outside of a cloud in terms of virial boundedness, in terms of turbulence level. This is another way we have been having in mind. So there are a few ways to tackle this magical scale or non-existence of magical scale, but I think there are ways to understand the physics even despite that.
I have one question.
Yeah.
So in one of your slides, you showed that the star formation efficiency is lower in the fog regions compared to the outskirts. But my impression from the Fuheng's collaboration is that when they consider the variation in alpha CO conversion factor, sometimes they can lead to an enhanced star formation efficiency in the centers of the galaxies.
Yeah.
So I'm just wondering, in this community, has this issue been settled yet? Whether we expect higher or lower star formation efficiency?
I see. Yeah, that's a very good question. In this community, we don't call it an issue, we call it a feature, because even without considering the variation of alpha CO parameter from intensity to gas mass, we already observe a wide variety of star formation efficiency in the center of a galaxy. Sometimes it's enhanced, sometimes it's suppressed. It might be even similar to your work of post-starburst galaxy when it enters Green Valley. I don't know if it's entirely connected or not, but we do see a wide spread of star formation efficiency if we have a large enough sample of galaxies. And for this galaxy in particular, we see about 1 dex of increase in depletion time. So this is roughly 1 dex in difference, which is 10 times. But the alpha CO parameter, I think Ida is the expert here, but from my impression, it's usually a factor of 2 or 3, depending on metallicity. Although the formal error we quote from Bolotto 2013 review is 30%, but I think 30% does not account for the systematic variation, which can be a factor of 2 to 3. But still, this is smaller in extent than 10 times. So yeah.
There's a galaxy to galaxy variation.
Yes.
In terms of the radial profile.
Radial profile. Yeah, I think that's true.
So just to see if I follow what I should be thinking of now. So in the Hubble diagram, there are 2 basic branches, barred and unbarred.
Right.
And I would have thought that dynamically, barred means that your potential is not axisymmetric. And in a non-axisymmetric potential, there is no circular stable solution for the gas, I think, meaning that you must have gas. The gas cannot run in a circular orbit and will go in because the bar rotates at an incremental speed with your system, because you're rotating. So I would have thought that therefore, maybe that's what you said, I'm not quite sure I heard you, that therefore the disks in any capital B object will be much less regular than in a small b object. Is that what you're saying, or is that not what you're saying?
With a bar present, I think, yes, the gas will distribute with more disturbances, because the bar does induce, like you said, radial motions rather than circular motions, and both galaxies I showed have bars. So indeed, we see a lot of disturbances.
At 0, I thought it looked very regular.
The galaxy here has a very weak bar. So this is indeed regularly rotating. But it's slightly a different scale because the gas disk is only in the central region of the galaxy. So the bar may not play a major role because it's already migrated inward. But if we look at spiral galaxies, which I show here, this bar here certainly plays a major role in funneling the gas inwards. So this is kind of a slightly different stage when we look at the gas disk. And also the origin of the gas is probably different. In the other lenticular galaxy, the origin is recycled stellar mass. So recycled stellar mass follows the stellar disk. It rotates well.
From the previous path here, is that you say things are complex, and to me it means complex means we don't understand things. I'm hoping for simple things to be simple, meaning just something, a simple thing I should be remembering from today's talk, and I'm not quite sure what that is. maybe I'm learning that, the bar causes AGNs because of this irregularity, or that's not what you're saying, or that is what you're saying.
I hope the community would be confident in drawing such a simple conclusion. But from my own perspective, I think different physics are at play when we look at the same galaxy because...
But you don't have bar on this picture, so I'm not sure if that's...
Exactly, that's part of the gravity, I believe. If we extend this plot to 1 kpc scale, I think at 1 kpc scale, gravity actually becomes more dominant again. And we still see a trend here. It should become more dominant here on 1 kpc scale. So from my perspective, it is indeed an interplay between different physical processes. And I'm not confident enough in saying a simple statement, A drives B, B is resulting into C. That's not my picture when I think of galaxy as an ecology system. But we do hope that we can disentangle different physics in terms of their contribution, in terms of their effects on the gas properties and star formation.
So let me ask a simple question. So if the one which has no bar, no star formation case, you see that much bigger velocity dispersion towards the center. What is the cause of the increase of the velocity dispersion?
The velocity dispersion in the center, maybe it's... Yeah, for example, when we look at this, it might be beam smearing, for example, especially in the very center.
Towards the trend.
The trend towards the center. It might be more turbulence, or it might be
What causes turbulence?
turbulence injection. Yes, turbulence injection. We have explored.
But you're not forming stars, why is there turbulence?
We have explored the shear effect to inject turbulence because shear is kind of tearing apart clouds, and when clouds are torn apart, there is kinetic energy being released, and this may cascade down, which is kind of the picture of turbulence. So shear might be one turbulence origin.
So if your Q is bigger than 1, this doesn't get you anywhere, right?
But Q is also...
Q is, in that region, Q is bigger than 1, right? So at the end of the day, it's not sustainable. You can do it very, very intermittently, but it's only when Q is less than 1, I can keep fragmenting and I keep transferring it, but if Q is bigger than 1, this does not energetically get you anywhere.
Yeah, I mean, it's interesting that a collaboration...
It goes the wrong way, by the way. The Q is bigger on the inside. That's what you measured.
Yes, yeah, I remember that profile I showed.
In the middle,
I understand the fact, but what's the cause?
That's a good question, but his answer is not the cause of it. We know what it's not. We know what it's not. We don't know what it is.
Actually, some reason is many years ago we did some simulations without anything star formation, but still have energy source, which is type 1 signal. So I didn't publish a paper, but it shows that we have type 1 signal that pops up, from all stars.
All stars, yeah.
Which is plenty of them.
Yeah.
Nobody really care about the type 1 signal, okay? But actually it's doing the work. Even doing the heating, doing any injections, which can actually produce disturbance to the hot gas and the cold gas as well.
Okay, so that would imply that the star to gas ratio should matter.
Oh, yeah.
Which you can plot. What's the ratio doing in the middle?
Oh, it has to be great because
spatially resolved, I'm not sure. I'm not sure spatially resolved.
And probably it's going up because this
instead of gas, the stars is the power.
So the star dominates in the center.
That's not the gradient, not just on, but it keeps increasing, so you have to
overall
explain going up. So there's more gas, there's more stars per unit gas, and therefore you can pump more energy.
Exactly.
Towards the center. So that's indeed a feasible way to inject turbulence, yeah. And of course, we looked at cloud collision as well. But to produce higher line width, it can also be a line of sight confusion of multiple components too. If we have two clouds, they each have low turbulence, but the plot would show...
Actually, the pieces tend to be thinner towards the center, right?
Yeah, for this galaxy, it's not very likely because it's relatively face on. Yeah, so we do not worry about line of sight confusion, except in the very central part, because it can still be.
No, forget about the very central part. It's overall trend. We clearly see overall trend from outer towards the inner region. So that's not the nuclear region. So we talk about the overall trend.
Yeah.
That's simple, right?
Yeah.
More interesting.
Yep.
Too complicated is difficult. Not too many facts. But this one actually, you choose that one, it's great. I think you make a very simple case. You see the trend. Now you need explanation.
Yeah, I don't know if we can see supernova remnants from ionized data.
Simple calculation. You know the mass
from stellar density.
Yes, it's
stellar density.
Stars, they don't do too much.
They have to explode.
Yeah, they have to explode.
Yeah,
So
that would be one way to.
Rate based on the mass of stars.
Yeah. Thank you.
Just commenting on somebody was being involved in some supernova simulations. If you try interstellar meaning turbulence and supernova, you will not see most of the time the supernova bubbles anymore. They will mix up.
I see.
In longer time, and then actual supernova bubbles, yes, they are there, but they are not like the thing is supernova and turbulence. It's more longer time energy input.
I see.
Mixing up the ISM.
So even though we do not see signatures of bubbles, they still can be mixed already. Yeah.
No, you need a hot gas there.
Yeah.
So they need to be heat. The gas needs to be heated. Now, without heating, it cools down very fast. So the energy source there. Ideally, if you don't have AGN in the middle, that makes things even simpler.
There is a low luminosity AGN in the middle, but
okay, probably it doesn't matter much.
Okay, good. Now we had a very lively discussion. So Eric will still be here till tomorrow noon. So feel free to ask him questions in 11:08. Okay, let's send Eric again.
Thank you.